Okay, I'm going to keep talking about topic 4, multivariate normal, and let's see. So I hope today to get to the portion of the notes in topic 4 that have to do with maximum likelihood estimation. So if you've had other statistics classes, chances are you've been exposed to maximum likelihood or MLEs. They're a particular way to estimate a parameter that is sensible and mathematically good. So what we've seen last time and this week is the multivariate normal. This slide 5 has the probability density function. It's a generalization of the univariate normal. And remember, we've got a constant out front and then an exponent term. So e to the minus a statistical distance divided by 2. So f of x, whenever x is, quote, far away from mu, that is going to translate to a statistical distance between x and mu that's big, positive. So for an x value that's far away from mu, this e to the minus the distance will tend to be small. That just means that the elliptical surface that represents the PDF will be close to 0 in regions that are far away from the mean. It's analogous to the univariate case. If this is a univariate normal centered at mu, standard deviation sigma, the closer we are to mu, like this particular value right there, x1, is close to mu. And the closer you are to mu, the taller the probability function is. There's more probability density around points that are closer to the mean. And the further out you get, like this point, that's very far away from the mean, the PDF is going to be really close to 0 at that point. So what I was just saying on the topic 4 slides is analogous to that. If I have the bivariate case, for example, x1 and x2, here's the probability density function, and suppose the mean is right there, mean vector, and we have a elliptical surface like that, then a point x1 that's pretty close to mu will have a lot of volume on top above it, whereas a point x2 that's very far away from the mean will have volume, very little volume above it. So you're more likely to see x1 if you randomly draw from this distribution than you are to see x2. And that's a consequence of the probability function itself having statistical distance in it. Okay, so here, I can't remember if we touched this slide last time or not, but let's talk about, for a multivariate normal distribution, where are the regions of constant distance from the mean? We've done this before, not restricted to the multivariate normal, but for an arbitrary distance calculation, for an arbitrary weighting matrix A. Here it's sigma inverse, but for an arbitrary A. We know how to find the the points that are equidistant from the origin. It's an ellipse, and we've seen that the primary axes of that ellipse are the eigenvectors of the weighting matrix that's in the middle of the quadratic form. And the half-lengths of those primary axes are proportional to the distance and the square root of the eigenvalues of the weighting matrix. This slide right here is then review. We already know how to do this. For this particular quadratic form, the statistical distance is a quadratic form. It's something transpose, a vector transpose, a weighting matrix times the same vector. In our case, it's x minus mu transpose. Our weighting matrix is sigma inverse, and then x minus mu again. So suppose we want to find the points that are squared distance c squared away from the mean vector mu in the multivariate normal. Then we know how to handle this. The or the principal axes, let me just write it down. Takes a couple of times writing it down for it to click, I claim. So for multivariate normal, p-dimensional, with a mean vector and a covariance matrix, the points that are equidistant from the mean are on the ellipse given by x minus mu transpose sigma inverse x minus mu. So let's say that E1, E2, ... EP be the eigenvalue or eigenvectors. Let these be the eigenvectors of sigma inverse, our weighting matrix. And similarly, let lambda 1 through lambda p be the eigenvalues. So the ellipse, I needed to provide the distance. The ellipse is defined by statistical distance, squared statistical distance, equals c squared, where c is the distance that we want to go out equally around the mean. So with this information, the ellipse of points constant distance c from the mean. They have primary axes E1, E2, EP. And they have half lengths c divided by the square root of lambda 1, c divided by the square root of lambda 2. That's a direct result of what we saw in topic 2. In the notes, So have to be a little bit careful. The main thing that I want you to keep track of with it, when it comes to this ellipses of constant distance from a mean, remember the basic definition. That was that x transpose AX, if you want that to equal c squared, then you get the eigenvalues and vectors of A. So lambda I, comma, EI. And then the primary axes are the EI, and the half lengths. So primary axes are the EI, and the half lengths are c divided by the square root of the lambda I. So whatever A is, if you get its eigenvalue, eigenvectors, then you know the primary axes are just the eigenvectors, and you know the half lengths of those axes are the distance, c, divided by the square root of the eigenvalues. So if you read this slide, there's the potential for confusion. Let me just point out where that is. The slide says the ellipsoids are centered at mu. That's not confusing. That's where we would expect them to be centered. But they have axes plus or minus c square root of lambda EI. That's another way of saying that the directions of the principal axes are the EI, and the half lengths are c times the square root of eigenvalues. That's a little confusing, potentially, because didn't we say it should be c divided by the square root of an eigenvalue? There's nothing incorrect. It's just that what I'm saying here is that E and lambda are the eigendecomposition of sigma, not sigma inverse. So depending on how you define, what are you working with? Are you working with the eigendecomposition of sigma or that of sigma inverse? Just keep track of the basic definition, and it will tell you whether to divide or multiply. Whatever the weighting matrix is, that's what you get eigenvalues, eigenvectors for. And then you do constant distance divided by square root of eigenvalue. In our case, we have a sigma inverse, so I could go get the eigenvalue, eigenvector decomposition of sigma. And because the eigenvectors of sigma inverse are the same as those of sigma, we have the same principal axes. And the only difference between the eigenvalues is that the eigenvalues of sigma inverse are 1 divided by the eigenvalues of sigma. So I tried to clarify in what remained of this slide. If it's confusing to you, just remember I'm trying to point out that you have to be careful whether you multiply or divide by the eigenvalues, and it depends on what did you do the eigendecomposition of. The basic principle I recommend that you draw from here. Whatever A is, that's the pieces that you use in this way. I'll skip this slide for now. Then I have some slides that are more illustrations of what a bivariate normal distribution looks like. So here's an example where again, it's bivariate, x1 and x2, just two variables. And the variance of variable 1 is the same as that of variable 2. equal variances. But there's positive correlation. The bivariate normal distribution, the elliptical pattern shape surface that represents probabilities, looks like this. So notice it's not spherical. The impact of having correlation is that what would otherwise be a spherical distribution gets kind of pinched. As x1 changes, x2 is kind of restricted in what it can do. Because of the correlation, x2 is restricted to follow x1 on average. So instead of spherical, you get x2 kind of pinched in following x1 more closely. Here's the spherical case, equal variances and no correlation. In that case, statistical distance is the same thing as Euclidean distance. Statistical distance is all about accommodating unequal variances and correlations. Here's a picture for equal variances and negative correlation. It's useful to know what some of the canonical forms of these distributions are. So if you have bivariate data and you make a scatter plot, you'll know what it's showing you. Oh, this picture is what it looks like when I have negative correlation in the data. Here's a picture when the variance of variable 1 is bigger than that of variable 2, and there's no correlation. So correlation, if you look at the last few figures, correlation is about angle. It's about angle of rotation between these two variables, their distribution. Differences in variance is about spread on the horizontal or vertical axis. So if x1 is more variable than x2, then it's going to be spread out on the horizontal axis more so than on the vertical axis. Here's a combination of both of those distinctions. Sigma 1 is bigger than sigma 2, so you have the horizontal variability bigger than the vertical, but you also have positive correlation. So in addition to that flattened out ellipse, it's rotated some in a positive angle. Here is the flip side. This is sigma 1 less than sigma 2. So now variable 2 has greater variance. So you have a kind of flattened out ellipse that varies more vertically than it does horizontally. And there's correlation, but there's negative correlation. So notice that it's not actually leaning in a negative direction. It's leaning in a negative direction relative to the line of equality. So just looking at a scatter plot or a contour plot of the distribution of two variables, I guess one takeaway message is that you have to be a little careful about interpreting what exactly it's showing you. It can be a little bit counterintuitive. This is negative correlation, which is a little bit counterintuitive because the distribution is not oriented with a negative slope. Let me open up our script real quick. We were in here yesterday, or Monday. And let me just run a little bit of this code if I can. I think we don't have plot tricks. And I think if I try to install a package on this computer, it's going to complain. Package. So to install a package like plot tricks, I want to use a function that didn't come with the built-in base R it's specific to this additional package called Plotrix. In order to install a package, I can go to Packages, Install Packages. Then I pick a download site that's close to me, and go find what I want. Okay, so let's see if that works for us. Oh, good. Okay. In the topic 4 script, topic4.r, beginning line 17, I have code that makes these pictures. I'm going to make use of a function called draw.ellipse that is handy for drawing ellipses. I think I talked about this briefly in the Q&A, but the way I'm going to use draw.ellipse is first I'm going to tell it where's the center, where's the origin of the ellipse. And for us, that's the mean. With 2 dimensions, it's mu1, mu2. That's the center of the ellipse. Then I'm going to tell it half lengths of the major and minor axes. And then I'm going to tell it the angle to rotate. You can also provide the actual eigenvectors. When I originally figured out how to use draw.ellipse, I found it easiest to work with the angles. So one way to use draw.ellipse is to figure out what's the angle between the eigenvectors and the original xy axis. So basically this is saying go to mu, that's the center point, then go out this amount for the primary axis and that amount for the secondary axis, and then rotate the whole thing by the appropriate amount. Just so that we've gone through this together, the way I'm doing this is because I wanted to make pictures for several different bivariate normals. There's 1, 2, 3, 4, 5, 6 of them. An efficient way to do the same thing with 6 variations on it is instead of having 6 chunks of code that do the same thing just with minor differences, is to create your own function. If I create my own function, then I can put down one time code that given a mean, a covariance matrix, and I'll talk about that in a second. Basically, given a mean and a covariance matrix, will plot that ellipse that I want. So inside here is all generic code for an arbitrary mean mu and an arbitrary covariance matrix sigma. Then down below, I can just say call ellipse f with whatever sigma I want. So there's one example of a sigma. Here's another example. And I just call ellipse f multiple times instead of having to copy paste that big chunk of code up here. So this function takes 3 arguments, mu, sigma, and alpha. What alpha
is a restriction on how far out to go. We're going to, basically, ellipse F is going to draw the ellipse of points that are constant distance from mu, assuming a bivariate normal. So do you want it to be really close to mu, or do you want it to be a big ellipse? Alpha is going to be how I dictate that. Alpha is intended to call to mind critical value kind of alpha. Like, because this constant distance from the mean is going to play a key role when we do confidence regions that are like multivariate versions of confidence intervals. So for a confidence interval, the width of it depends on how confident do you want to be. Do you want a 95% confidence interval, or a 99%, or an 80%? And we use this alpha to indicate 1 minus your confidence level. So a 95% confidence interval would be a confidence interval with alpha equal 0.05. That's where the notation is coming from. So inside my function, I give it mu, a vector, sigma, a p by p matrix, and alpha, a scalar between 0 and 1. I'm going to make sure I know what the dimensions are. I can get that from the length of mu, or I could say the n row, number of rows of sigma, or the number of columns of sigma, multiple ways to do that. What you saw in your homework, and we're about to see in the slides, is that the chi-square distribution plays kind of a magic role in finding these ellipses of constant distance with a multivariate normal. So it shows up here. I'll mention in more detail why it's here in the slides momentarily. But I'm asking for a distance. This is going to be the square of the constant distance, and it's a function of alpha. So do you want a really wide ellipse or a really tight ellipse, depending on the choice of confidence level? And then here's the gory details. In order to do these ellipses of constant distance, what I need are the eigenvalues and eigenvectors of the sigma matrix. Either sigma or sigma inverse. And depending on which one you do, you know whether to multiply or divide by the square root of the eigenvalue. But the eigenvectors stay the same. So if I were rewriting these scripts, I would probably do sigma inverse, just because it's one less little complication. You don't have to think as much. But when I wrote these, I used sigma. So we can still do that. I'm going to create an object, EE, that is the result of calling eigen on sigma. So in EE are now two elements, the eigenvalues and the eigenvectors. This values is a vector that contains p elements. The first element is the first eigenvalue, second element, second eigenvalue, and so on. This piece called vectors is a matrix. And each of its p columns contain eigenvectors. So the eigenvector matrix here is a p by p matrix, and its columns are the eigenvectors. First column is the first eigenvector. Second column is the second eigenvector, and so on. So I'm just pulling apart these pieces so that I can refer to them easily. Lambda are the eigenvalues, and EE, I renamed that to just be the matrix of eigenvectors. Where in the world did this come from? It is an application of something we saw in topic 2 very briefly. So we can talk about, here's a picture of two vectors. You have the x-axis, y-axis, and then you have the longer directed line segment called x, and the shorter one called y. One way to characterize an arbitrary vector is what's its angle with respect to the original Cartesian axis, theta 1 in this case. Or what's the angle of y, theta 2 in this case. Or in some cases, what's the angle between two vectors, two arbitrary vectors, theta. There's some analytical results that allow us to get angles. So in particular, the general representation of an angle between two vectors, call it theta, the angle between one vector and another vector. I can compute that through this relationship here. The cosine of that angle is equal to x transpose y divided by the length of x times the length of y. So basically, the cosine of the angle is the cross product of x and y normalized to be of length 1. I'm not particularly, I don't particularly care that you do much with computing angles. So let me just tell you this expression is computing the angle using what we just saw on the slides. In particular, the a cosine in R is like inverse cosine. So if the cosine of the angle is that inner product of x and y divided by the product of their lengths, I could compute that vector operation, and that would be the cosine of theta. If I want then theta, I need to kind of undo the cosine. That's what a cosine is doing. So basically, I'm saying solve for theta from an expression that tells me what cosine of theta is. This piece here comes from the fact that what I need for rotating my ellipse is the angle between the x-axis and the primary axis of the ellipse. So the expression from the notes actually simplifies a little bit. And all you actually need is the first eigenvector. So I'm not going to go into the details of that, but this comes from this calculation. You can ask, what's the x transpose y divided by length of x, length of y, comparing the first eigenvector to the horizontal x-axis. And then this right here is just a conversion factor to take degrees. Wait, what is it? Degrees. Radians to degrees, right? Yeah. This is a conversion factor to take radians to degrees. So 2 pi radians is 360 degrees. And I need it in degrees. In order to use the angle argument from draw ellipse, if you look at the help file, it's expecting degrees. Say again? Sorry, I can't hear.
Inside draw function, you put degree equals false, so that the elevated aspect.
Oh, inside the draw dot ellipse? If you say degree equals false? Okay. As with most things in R, there's multiple ways to do most of everything. So you can apparently avoid making this conversion if you use another argument to draw dot ellipse to make it work with radians instead of degrees. The other function that I created, just FYI, if you look down further, once I've defined my function ellipse underscore f, it's ready to be used. One of its arguments is a covariance matrix. Okay, so whenever I call ellipse underscore f down here, I need to give it as the second argument a covariance matrix. And again, just as a time-saving feature, so I didn't have to repeatedly type matrix concatenate stuff in row equals something, I created an in-between function that only requires that I provide the standard deviations and the correlation. So using those pieces of information, at least in the two-dimensional case, if you know the 2 standard deviations and the 1 correlation, you can use that to generate the covariance matrix. In particular, the first row, first column is the variance of variable 1. The second row, second column is the variance of variable 2. First row, second column is the covariance between variables 1 and 2. Where does that come from? That a particular expression? Let me just fill in the blank on that one. We know that, so if x is a bivariate random vector with mean mu and variance matrix equal to sigma, oops, we know that the covariance between x1 and x2 is equal to sigma 1, 2. That's the definition of sigma, little sigma 1, 2. And we know that the correlation between x1 and x2 is equal to the covariance between x1 and x2 divided by the square root of the product of their variances. So another way of writing that would be sigma 1, 2 divided by the square root of sigma 1, 1, sigma 2, 2. In my R code, I'm defining the covariance matrix using the 2 standard deviations and their correlation. But sigma is in terms of covariances, not correlations. So you can go backwards from a correlation to get a covariance, just like you can go either way. So given a correlation from this, I know that the covariance is equal to rho times the product of the variances. Just algebra, solving for sigma 1, 2. That's where this came from. The covariance between variables 1 and 2 is equal to the correlation times the product of the standard deviations. So once that's all done, let me create this function as well. Then I can make a picture. Since I'm going through all the details of the R code, let me make another comment real quick. When I call that command, it's going to create a new plot panel and put the ellipse. So let's go ahead and do that. I made my function ellipse f capable of taking multiple alphas. So here I said, give me confidence ellipses for alpha equal to 0.1 and 0.5. So one of them is a 90% ellipse of constant distance, and the other is a 50%. Which one is the 90%? Just as a sanity check. The red one. Further you go out, you capture more and more of the distribution. Okay, so there's a picture. And then I have another command called title. One of the exceptional characteristics of R is graphics. It's excellent at creating graphics. Part of the reason for that is that you can customize things very easily, relatively easily, down to the very minutest detail. What size tick mark do you want on the axis? How many lines from the axis do you want the X label? Do you want a legend? If you want a legend, do you want a box around it or not? What size font to use? What colors to use? A title? All types of things. So one function, many of those add-on features for customizing are done after you create a base picture. So ellipse F just made a base ellipse picture. And now I want to add a little bells and whistles. So what I'm going to do is use the title function. And if you look at the help file for title, what it does is add a title up top or an x-axis or a y-axis label, depending on the syntax that you use. It adds those things to an already created base plot. So I'm going to say title, and I want a main title. That means up top, across the top of it. Another nice thing about R is that on the graphics, you can use mathematics notation. So in the slides, notice that I've got Greek symbols. Sigma 1 equals sigma 2, and rho is bigger than 0. You don't have to know how to do this for the purposes of the class, but if you're going to use R more in the future, check out the expression function. Expression allows you to, for example, spell out Greek symbols or Greek letters, and it will translate them to the actual Greek letters. You can also do some mathematical operation symbols. So when I call this, we're going to get a title. Currently, there's no title. So now there's a title. Okay. Let's end with this slide right here. Multivariate normal. Suppose we have data that we think are multivariate normal. There are some basic operations that we can do with that type of distribution. So there are things that we know include the following. So linear combinations of the components of our random vector. Like if x is bivariate, we have x equals the vector x1, x2. What if we did, say, a times x1 plus b times x2, a linear combination of my variables? Would that be normally distributed? The answer is yes. So linear combinations of multivariate normal variables are themselves normal. Also, subsets of the components of the random vector. Like suppose we have x1, x2, x10. If I were to take just x1, x2, x5, that will also be multivariate normal. It'll be a 5-dimensional multivariate normal. Conditional distributions. We'll talk about this a little bit next time, but Stat 101, you learned how to do conditional probabilities. What's the probability, or what's the distribution of heights among U.S. adults? That's one question. Another slightly different question would be, what's the distribution of heights conditional on min? The first distribution is with respect to the entire population, men and women. The second one is a conditional distribution, because I'm subsetting the population I'm looking at. Conditional probabilities we'll see, and the nice thing is that when you do, if you have a bunch of variables that are multivariate normal, if you condition some of them on some of the others, you get multivariate normal. And then the other kind of specialized result for multivariate normal is that no correlation means statistically independent. And that's not generally true. It's possible with non-normal data to have two random variables that are not correlated, but they're not independent. So the only time you could say zero correlation means statistical independence is with normality. All right, I'll end there. What I want to get to as soon as we can is this, beginning slide 34. So if you're chomping at the bit for what's next, start at slide 34. Okay, see you Friday.